Alright, welcome back to the channel Code Labs. Today we are going deep into the binary search trees. So by the end of this video, you clearly understand what a binary search tree actually is, why traversal matters, in order, pre-order, post-order properly, and most important part, how to reconstruct a binary search tree from traversals. So in this whiteboard, I have written that the binary search tree equal to a ordered binary tree because I state that because the binary search tree gives the output in an ordered way, like in ascending order or in the descending order. So I have drawn a binary search tree in here. You will can't understand now, but I simply explain what is because in the uh, further referencing we can understand why this. So in here 40, in your left hand side it is 20, smaller than the 40, and in your right hand side it is 60, uh, bigger than 40. Like that we are dividing the binary search tree when we are inputting data. So first thing first, we'll understand what is a binary search tree. A binary search tree is not just an tree, it follows strict rules. If you miss these rules, everything collapses. Rule number one, every node has a unique value. You can see in this binary search tree, the data is not duplicated anywhere. All the data is unique for every node. Rule number two, this is the soul of the binary search tree. All values on the left hand side are smaller. You can see 40, after that 20, smaller. And in the left hand side, in the subtree of the 20, 40, 20 subtree in the node 20, you can see the value on the left hand side is 10, smaller. But on the right hand side, the value is 30. That's right. In the right hand side, the value should be larger or greater than the value in the node. We can see that 40 in the left hand side of the 40 there is 60, but in the 60's right hand side it has 50, in the 60's left hand side we have 70. So like that we can draw a binary search tree, and this rule doesn't apply once, it applies recursively. You can see the left hand side, right hand side rule is applied everywhere. That's why it's called a search tree. We eliminate half of the tree at every step, just like a binary search. Like this. You can simply memorize this as left smaller, right larger. Left smaller, right larger. So, why do we even care about the binary search trees? Because they give us faster searching. Like, unlike the other binary search trees, it allows significantly quicker searching by eliminating half of the remaining nodes at each comparison. Efficient searching operations. Insertion deletion of elements are highly efficient. Sorted data without extra. I said that in the beginning of the video, the data is given in a sorted way, like in an ascending order or descending order, as a user wishes. So we can identify the each data very easily without again reorganizing the given data. So binary search tree traversals. Traversals simply means how do we visit nodes. There are three classic traversals, like in order, left, root, right. Pre-order, root, left, right. Post order, left, right, root. Here I state left, root, right. In order, pre-order, root, left, right. In order. Visible the left subtree, then the root, then the right subtree. Pre-order visits the root first, then the left subtree, and then the right subtree. Pre-order traversal. Left, right, root. Visit the left subtree, then right subtree, then the root. Every traversal technique offers a unique sequence of nodes, providing a distinct insights into the binary search tree's organization. Understanding these differences is crucial for the tasks like reconstruction and validation. So nextly we have to talk about the in-order traversal. So in-order traversal is special. For binary search tree, in-order traversal always gives sorted output. If it's not sorted, that tree is not a binary search tree. Memorize, if the data given in a in-order traversal is not sorted, there is that tree is not a binary search tree. So like this, we'll get a data set and we'll talk about, and then we'll further continue why that data set. So in here I have a given data set like 10, 20, 30, 40, 50, 60, 70. Like this. The data is given in a sorted manner, like 10 after that 20 greater than 10, 20 then 30 greater than the 20, like that. This is given in an ordered manner, then it means sorted. In a in-order traversal, it is always ordered. The sorted output is invaluable. If you perform an in-order traversal on any binary tree and the output is not sorted, like I said earlier, then the tree is definitely not a valid binary search tree. This makes in-order traversal a quick and effective method for binary search tree validation. As I given in the PDF for the presentation, the binary search tree divides the 20 into the left hand side because smaller and the 50 to the right hand side. Like that, it divides the data by left hand side, right hand side as the value is greater or smaller. So what is a pre-order traversal? Pre-order is root first. This is huge when building or copying trees. First value is always the root, no guessing, because in this 40, 20, 10, 30, 60, 50, in this data set, the root will be the first, then after that it will be divided into subtrees. So we will get this data set in the whiteboard. Firstly, we have 40, 20, 10, 30, 60, 50 and 70. So in here, what is the root? Root is the 40. 40 is the root. So that will be never change in the pre-order traversal. Then the left subtree, all the values appear after root are smaller, like 20, 10, 30. They are all small. This is very special in the pre-order traversal. After the root, the data is smaller and the right subtree values. If we divide this into a binary search tree, like in the binary search tree above, the data 20 then 30 come into the left hand side because they are smaller than the 40, and the values in the right hand subtree are gaining 60, 50, 70 because they are larger. If we draw this binary search tree as a tree I drew in earlier, 40 comes in the first because it's the root. This is not changing. This is a stable of the pre-order traversal. This will be never changing. First value is the root. Then secondly, 20. 20 is smaller than the 40. Then it comes to the left hand side. This rule will be never changed, that the left hand side gains the smaller values than the previous node or previous value. So next is 10. 10 is smaller than 20, and next after the 10 we have 30. 30 is greater than 20 but smaller than 40. Because of that, 30 cannot be written in the right hand side because 30 is smaller than the 40. But when we get into the 20, 30 is greater than the 20. So we can write the 30 in the right hand side. So now this data is being sorted. Now we will get to this data 6, 50, 70. So in these 60 is larger. So it comes to the right hand side. After then 50. 50 is smaller than the 60. So it comes to the left hand side. 70. 70 is greater. So it comes to the right hand side of the root. Like that is the order of the pre-order traversal in a binary search tree. So next we'll visit to the post order. In a post order traversal, we'll get this data set into the whiteboard so we can explain it. So first we have 10, 30, 20, 50, 70, 60, 40. This is the data set we have. So in the post order traversal, the root is in the last. In the pre-order, we have the root in the first. But in the post order, we have the root in the last. And in the in order, the root is root is the first. Like in order, the data set is always sorted. Now this is not sorted. You see 10, 20, 30. So this is not sorted. So we can get the root as 40 because it's the last. So this is the root. 40 is the root. So nextly, now we have get the root. So we will draw it in the first node as the root node. And left before right. Values corresponding to the left subtree always appear before the values from the right subtree relative to their common parent. Like in here, next we should get 20. Left before right. Always getting the left before the right. So left we get here 20. And next we are getting the 10 and we are getting 30. You can see that this data set is in here. This subtree can get in here. The root is here. And the right subtree, this 50, 70, 60, this data set, we can see that the data set is being separated, but we have to find, we should be able to find that using the rules that I said earlier. So we can get this subtree like 40 larger 50, no 60, sorry 60, then 50, then the 70. So like that we can get the post or the traversal this way. Always in the pre-order, the root is in the first. In the dataset, the first element or the first value in the dataset is the root. In the post order output, in the post order dataset, the root element is given in the last. Then you have to find the subtrees for that relevant root element. So now we have to reconstruct a binary search tree from the pre-order. So now we are in the box level. Like one of the most remarkable properties of a binary search tree is the ability to fully reconstruct just its pre-order using the traversal sequence. This is possible because the binary search tree's inherent ordering rules, left, root, right, provide sufficient structural information, unlike general binary trees which often require traversals. So identify the root as in the pre-order, the root becomes the first value in the data set. So 40 is becoming the root. So partition of the list structure. Scan the remaining sequence to find all elements smaller than the root. These from the pre-order sequence for the list structure. For 20, 30 and 10 are the small. Partition for the right. So partition for the right is the larger 50, 60, 70. Apply these steps recursively to the left and right subtree sequences until all the nodes are placed, like 40 coming, then 20, then 10, then the 30, then the 60, 50, and then the 70. So like that we can reconstruct a binary search tree from the pre-order. So lastly, we are coming to a conclusion and we are ending the topic binary search trees. How to construct, reconstruct the binary search trees. So the binary search tree rule, the core principle, left child, parent, right recursive, like that. Order, I said that there are two rules. The left value and the right value. The rules are in the pre-order, post-order. They are all coming together when we are making a binary search tree in order traversal. Like always produces elements in a sorted order. A key for validation. So, in the in-order traversal, the data is always sorted. As I said earlier, the data is not like in an unorganized manner, always in a sorted manner, in an ascending order or maybe in the descending order, like that. Pre-order and the post-order. Identify the root's position. Like in the pre-order, always root is in the first, then the values, then the after the value, the values after the root are becoming the subtrees. In the post-order, the value at the last is becoming the root and the other values are becoming the subtrees of the root. And the binary search tree reconstruction, a binary search tree reconstruction can be fully reconstructed from the pre-order traversal alone, only from the pre-order traversal, because it's unique ordering, because the root is in the first and then we can find the other subtrees from the values. Predictable behavior. Mastering these cases makes problems and applications much more predictable and manageable. Uh, okay, now we are coming to an end of this video. So thank you coming along with this journey. Have a nice day.